Okay, guys, welcome to Physics 203, Class 26. And this class is on time dilation, length contraction, and addition of velocities in the uh, relativistic way. So we'll see here some very unusual consequences of Einstein's postulates that the speed of light should be the same in all reference frames, and that the laws of physics should be the same, should be observed to be the same in any inertial reference frame. So here's where things start to get weird and interesting. So we start off with an effect called time dilation, and here is two reference frames, a system K and a system K, which is here with Frank in it, and a system K prime with our character Mary, and system K prime is moving to the right with respect to system K with a velocity v. And we imagine that in system K, Frank lights a sparkler, like let's say it's the 4th of July, and in that frame, the sparkler burns and goes out, and that all occurs at the same position, x1, in system K. So, so Frank doesn't move, and the sparkler lights and goes out at the same position. So we define the proper time as the time between events which occur at the same location in a given frame as measured by one of that frame's clocks. So an example of this is what we were just talking about. Frank's sparkler here being lit and then going out, since it occurs at the same location in this frame, the location x1, both the lighting and the extinguishing of the sparkler, the time that passes on Frank's watch would be termed a proper time. So, however, for the moving system, K prime, where Mary and her friend Melinda are, you can see that the sparkler lighting and going out occur at different locations. The sparkler lights when Mary is at even with Frank, but it burns for a while. This system K prime moves to the right, and by the time it goes out, Melinda, who's at a different position in that frame, x2 prime, is even with the sparkler. So the time measured by a clock in the prime frame would not be a proper time, because the sparkler does not, it starts burning at position x1 prime, where Mary is, and it ends, it goes out at position x2 prime, where Melinda is. So the question becomes, if it's not the proper time, is it the same time interval, or is it, how does it differ? So what is the time interval t2 prime minus t1 prime as measured in this moving system? Okay, well, recall that we went over the Lorentz transformations last time, and the final last Lorentz transformation was from the unprime to the prime frame. T prime is equal to gamma times t minus beta x over c. And where gamma is 1 over the square root of 1 minus v squared over c squared, and beta is v over c. And this would apply to both events 1 and 2, that is, both to the lighting of the sparkler and the extinguishing of the sparkler. So to find t2 prime minus t1 prime, we apply this transformation to both the lighting at which is event 1, and the extinguishing, which is event 2. And we get T2 prime, which would be T2 minus V over C squared x2. That's the Lorentz transformation applied to event 2, minus T1 prime, and T1 prime is T1 plus V over C squared x1. So we get this over and all over gamma. So here's our expression from Lorentz transformations for T2 prime minus T1 prime. However, in this equation, x2 minus x1 would have to be 0, because in the unprimed frame in system K, the sparkler, the event happens at the same position. So x2 here would be equal to x1. So x2 minus x1 is 0. So therefore we find that the time interval in the primed frame, t, which we call capital T prime here, it's equal to T2 prime minus T1 prime, would be equal to the time interval in the unprimed frame, T0, which is the proper time, over this square root of 1 minus V squared over C squared, which is equal to, since gamma is 1 over the square root of 1 minus V squared over C squared, that's equal to gamma T0. Okay, so we see that Mary and Melinda in this frame, moving frame K prime, will measure a longer interval T prime than the proper time T0, because gamma, because of its the way it's structured, gamma is always greater than or equal to 1. And this is known as time dilation, okay? So we often express this by saying that moving clocks run slow, okay? Moving clocks run slow. And by that we mean that Frank's watch, not James's watch, but Frank's watch, which would be moving with respect to Melinda and Mary, will record a shorter time interval between events than will Melinda or Mary. So the shortest time which is recorded is always recorded by the proper time, the frame in which the two events, for example, the lighting and the extinguishing of the sparkler, or the ticking of a watch hand between, for say 60 seconds, occur at the same position. And so any other observers in a frame moving with respect to that proper time frame will will measure a longer time between those two events. And that's the surprising effect of time dilation. Okay, so that's really strange, and it comes from the Lorentz transformations, as we've seen, which in turn come from Einstein's two postulates, just applying the principle of relativity to all that it should apply to all the laws of physics. Okay, so another interesting effect is length contraction, and so just like there's a proper time, there's a proper length. Okay, a proper length is it's not a length which is very polite or always says please. No, it's a length which is the proper length is the length of an object measured in a frame where the object is at rest. Okay, so you can see here two guys here with a ruler in between them, and the ruler is at rest, and so they mark off the ends of it, and then they can, the proper length, since the ruler is at rest in that frame, it's not moving with respect to them, that determines it as a proper length. Now in the rest frame of an object like this ruler here, it doesn't matter what time the positions of the two ends are measured. Like this guy on the left could mark and measure this position, and then 10 minutes later, this guy could come over and mark and measure this position, and they could determine the distance between them. And because the ruler isn't moving, it's not going to change because of the time interval between the two measurements. However, if we imagine someone else, so we say that someone else is in a, say you are in a rest frame K, and that now these two guys in the ruler are moving along in reference frame K prime with a velocity v, so imagine these guys moving past you, then in order to make a proper measurement of the length, we need the measurement of each end to occur at the same time, okay? Because imagine that if we measured the left end at 12 o'clock, and then we measured according in our frame, and we measured the and you measured the right end at 1 o'clock. Well, this ruler would have been moving at velocity v, so it would be way over here, and it would appear to be much, much longer than it is. Okay, so so we find in order to make sense of the measurement, we need the measurement of each end to occur at the same time if we're measuring a moving object. Okay, so here to analyze this and to figure out the relationship of the moving length, or the length measured in the moving frame to the proper length, we use the first Lorentz transformation, which involves the lengths. So we have x prime equal gamma times x minus beta ct. And this will apply to both n1 and n2. Okay, so or we can say the right end and the left end if we want. So the difference, just applying this expression here to the right end and the left end, we find that the difference of the right position in the primed frame, xr prime, the right side in the prime frame, xr prime, minus the left side in the prime frame, xl prime, will be equal to the measured positions in our unprimed frame, in your frame, your rest frame here, minus v times tr minus tl. Okay, where tr is the time in your frame, in the unprimed frame, when the right side is measured, and tl is the time when the left side is measured. But we just said that in order to make a proper measurement of length, we need those two sides to be measured at the same time. So t2 minus t1 is equal to 0, and xr prime minus xl prime is equal to l0 prime. That is, the object is at rest in the primed frame, because the object is at rest in the moving frame. So we have L0 prime is equal to L, our length, the length in your frame that you're trying to determine, over the square root of 1 minus v squared over c squared. But 1 over the square root of 1 minus v squared over c squared is gamma times L. And so we get L is equal to L naught prime over gamma, but L naught prime is equal to L naught because all proper lengths are the same in every frame. So we get L is equal to L naught over gamma. So what does that mean? It means that an observer in the frame K, say you, measures a length L, which is shorter than the proper length L naught, shorter by a factor of gamma. Remember, gamma is always greater than 1. And that's known as length contraction, okay? So we can express that by saying that, if we like, by saying that moving rulers look long. So in the moving frame, the ruler has its proper length, but when we measure it as it's flying by, if we measure the two ends at the same time, we're going to get a smaller length. And so that's length contraction. So a ruler or any object will always be measured to be longest in the frame in which it's at rest, and it will be shorter and get progressively shorter as it's moving faster and faster relative to you. The final effect we want to look at, this strange effect in relativity, is the relativistic addition of velocities. Okay, so suppose we have a spaceship moving with respect to us on the planet Earth at a velocity of 0.9 c, and it's shooting out a laser. So there's laser photons that are moving out at the speed of light with respect to the spaceship. Okay, so it's blasting out at something. Our normal addition of velocities would suggest that the laser photons with respect to the Earth would move at their velocity c with respect to the spaceship, plus the velocity of the spaceship with respect to the Earth, 0.9 c. So it'd be c plus 0.9 c is equal to 1.9 c. But that seems a little funny to have something moving faster than the speed of light. So how do we resolve this? Well, we go back to the Lorentz transformations. Okay, these are our key to understanding how space and time events relate to each other in relatively moving frames. So these are the transformations from the primed spaceship frame back to the unprimed Earth frame, which we care about. So we're taking dx prime and dt prime as given and finding dx and dt, the time intervals in our Earth frame. All right, so these are the Lorentz transformations. And if we divide the first transformation by the fourth, we get dx dt, which we call u sub x, is equal to gamma times dx prime plus v dt prime over gamma times dt prime plus v over c squared dx prime. Okay, I'm just taking these equations and moving them over. The gammas cancel, and we divide top and bottom by dt prime, and we get dx prime dt prime is ux prime plus v, since the dt prime cancels here, over 1, since we're dividing top and bottom by dt prime, we get just a 1 here, plus v over c squared times dx prime over dt prime, which is what we mean by ux prime, the velocity of the object in the primed frame, that is, in this case, the laser photons with respect to the ship. And this is the relativistic addition. And notice we can also find, if we divide the second equation by the fourth and the third equation by the fourth, we see that the velocities in the perpendicular directions, so if the spaceship shot a laser down or out at us, the velocities of those would also be affected by the relative motion, okay, according to these formulas. So applying this to our initial problem, where we found a speed greater than c, applying this formula here, we would find ux, the velocity of the photons with respect to the spaceship, would be ux prime, the velocity of the photons with respect to the spaceship, plus v, the velocity of the spaceship with respect to the Earth, over 1 plus v ux prime over c, 0.9 c times c over c squared. So that'd be 1.9 c over 1.9, or just equal to c. And so we find, as Einstein's postulate says, we on the Earth would see the laser photons moving at the speed c, just as the aliens or creatures on the spaceship did. They saw those photons moving out at velocity c. So in this lecture, we've seen some unusual, using the Lorentz transformations and reasoning about times and lengths and velocities, we've seen some very unusual effects that there are proper times and proper lengths, and that moving frames see times greater than the proper time, and moving frames see lengths smaller than the proper length. That's time dilation and length contraction. And we've seen that we have to alter the addition of velocities to take into account, to keep velocities from becoming greater than c, the speed of light. All right, thanks for your attention, and I will see you in class.